Okay, 7.3, adding radicals. Semi-easy lesson, but a couple quirks, couple tricks that you've got to put in play. Done these before. When you think about adding radicals, just think about adding like terms. That's the concept. Adding like radicals is exactly like adding like terms. The radical is the same as the variable. So for example, you don't need to write this. We all know how to do 3x plus 2x. We all say 3 of them and 2 of them is 5 of them, it's 5x. So 3 times the square root of 2 plus 2 times the square root of 2, 3 of them and 2 of them is 5 of them, 5 times the square root of 2. That's all we're doing. You're just adding like terms, and you're just adding the coefficients. That's the concept, and that's the idea. So it's just like adding like terms, you're adding the coefficients. One thing you got to be aware of, only like radicals can be added, because again, only like terms can be added, right? And what are like radicals? Same index. I really wanted that to be red. It ended up green. Doesn't really matter though. And the same radicand. Look, can you add an x squared and an x cubed? And the answer is no, because they're not like terms. So can you add a square root and a cube root? No, because they're not like terms. They're not like radicals. So for them to be like radicals, it's got to be exact. Same index, same radicand. And then you're adding up however many of them there are. Just adding the coefficients. That's all you're doing. So that's what the rule is trying to show you. Add the coefficients, right? Add the a plus b. And I should do plus minus there, right? So I'm trying to show you two things at once. So the rule doesn't mean there's always a plus minus there. It means, okay, if it was a plus, it'd be a plus b. And if it were a minus, it'd be a minus b. And of what of them and what are they? The nth root of x, right? You just add the coefficients. Just add up how many there are. It's pretty simplistic. You're just adding the coefficients. That's all you're after. Okay, so again, first edition notes, just that shouldn't even be there. I was going to go one route and then I changed course and forgot to get rid of it and delete it. Okay, so, B. All right, this is really hard. 5 of them and 3 of them is like 8 of them. That's it. 5 of them and 3 of them is 8 of them. We okay there? All right, good. You're scaring me because I'm like, they're wondering what I did there. I really have a problem because I have no clue. All right, must be the voice. Whatever. Hopefully not something hanging out of my nose or anything like that. Okay, so just a small upgrade. Hopefully you agree we have all like radicals. Like radical, like radical, like radical, right? So we just got to add the coefficients. One little wrinkle, minus the minus, of course, we know is a plus, and that's not going to mess us up. So go ahead and add those up. Add those up. So 16 negatives and 9 negatives, 25 negatives and 10 positives leaves you 15 negatives, 15 of the 5th root of 2n's, right? Negative 15 times the 5th root of 2n. So in their simplistic form, that's not too tough. We can handle that. Not a big deal. Okay, so what happens is you get to a problem like this. And if I were you, I'd put an asterisk by this problem to remind you when you go back through and study and look at your notes. I don't know why I bothered to say that. None of you do that. No, a few of you do. When you go back and look at your notes, be careful of this kind. So right away you notice, okay, that's a like radical and that's a like radical, but the square root of 54, it isn't. Well, is it? Because you always have to look to simplify. So if we go to simplify, the square root of 54 happens to be a 6 times 9. Can we take the square root of 9? We can. We all know the square root of 9 is a 3, right? And we just got a 3 out. And so this is a 3 times 5. And now do you see how we actually have all like radicals? So you always got to be looking to simplify to see then if something will add. Otherwise, the problems are too boring. So 2 negatives and 9 negatives, 11 negatives, and 15 positives. So what do we got? 4 left. So you got 4 times the square root of 6 is the answer to that thing. If you can't add a radical, then you just leave it as plus or minus whatever that radical is tacked on. You'd have a couple. We'll get to that kind of stuff. Okay, so looking at E, what would you get with E? What would you do with E? So what do you got? 2i and a negative 5 times a 7i. So you got 35 negatives and 2 positives, which is 33 negatives. So you get a negative 33i is the answer to that one. So really simplifying that one got rid of all the radicals. All the radicals are gone. Any questions on that? I'm just trying to show you different possibilities of things that might pop up. Okay, so right away you look at F and you say, hey, there are no like radicals there. Well, are there? So you got to start simplifying this thing. What's a 75? 3 times 25. And we can all take the square root of 25, right? It's going to get a 5 out front. And a 12 is a 3 times 4. And we can take the square root of 4 and get a 2 out front, right? And we can take the square root of x squared and get an x out front. So where are we at right now? And again, some of you can handle it right now and finish it off. I just want to be clear for those of you that can't. You got a 15x times the square root of 3 and a 2x times the square root of 3. So now we have like terms in the coefficients as well as like radicals, right? So 15 of them and 2 more of them is 17 of the x's, and of them, square roots of 3, right? 17x times square root of 3. Is that okay with everyone? You're just simplifying and seeing what you got. See if everything simplifies from there. All right, try G. All right, so if you're done on 3, give me your solution. Here we go. 1, 2, 3. Okay. You guys need to ask a lot more questions then. If there's that many of you stumbling on a problem like this, honestly, you need to start asking questions. Because if you understand what's going on, this is really about a 20-second problem. All right, so you're going to simplify the front one. A 40 is an 8 times 5, and we can take the cube root of 8, right? You know, again, you're looking always to simplify. The cube root of 8 is 2, because an 8 is a 2 times 2 times 2. That gives you 6 times the cube root of 5. A cube root of 5 is a 1 times the cube root of 5. Just want to be clear there, right? So now we have 6 of them, and 1 more of them is 7 of them. And you can't do anything with the square root of 5. It's not like radicals, so that just stays. So 7 times the cube root of 5 minus 7 times the square root of 5. How many had that? Okay, so those answers were out there. You just weren't confident enough to verbalize it. All right, stop being such a chicken. Yes, Leah.
If the 7 times the square root of 5 would be a 7 times the cube root of 5, would it be 0?
Then you would have been 0. if that would have been a cube root, yes. 7 of them minus 7 of them, none of them, and there's nothing left. All right, any other questions? Okay, let's deal with some scientific notation. What are you owing about? Scientific notation is so easy. Look, all A is an addition problem. You're adding like terms. 3.5 of them, and let me box in the sign like I usually do, plus 4.1 of them. Gee, this is so hard. Like, how about 7.6 of them? It's just like terms. And where your brain needs to get to, look, this is the exact same concept. 3.5x plus 4.1x. Because that's a 3.5 times an x. What if x is 10 to the 7th? It's the exact same thing then, if x is 10 to the 7th. So just because it's written this way, don't let that mess you up. That's all that's there. Okay. The difference in B is our exponents don't match, right? Now we have a different issue because now they're quote-unquote not like terms, and we can't just add up the coefficients. So now you got to go all the way back to pre-algebra. And you guys don't remember much of pre-algebra, unfortunately. You definitely don't remember percents of pre-algebra, I can tell you that, because of the number of problems you missed on percents on the PSAT, and that was pre-algebra. But anyhow, that's another point. Okay, to get the same power, you need to change either the 10 to the 5th into a 10 to the 4th, or the 10 to the 4th into a 10 to the 5th. The best way is to change the smaller one and make it bigger. So if we're just going to make this now a 10 to the 5th, we've changed the problem. This has gone up by a power of 10. Instead of this being a 10,000, we just made it 100,000. We made it 10 times bigger. But it's this number times something 10 times bigger. So we're going to make this 10 times smaller. Which is simply to do what? Anybody remember? You just moved the decimal point one place to the left. And you just made it 10 less. So here's the shortcut. If you increase the exponent, you must decrease the number out in front by the same amount of places. If I were going to increase the exponent by 2 places, I'd have to move the decimal point 2 places to the left. It's just that simple. And so they go opposite directions. Okay, so now we can finish it off, right? Now we've got the same power of 10. And now you have 6.5 minus 0.9. If you can't do that in your head, then use your calculator, but don't get the problem wrong. And all you got to do is, right, that part, because we know it's going to be times 10 to the 5th, right? It's 6.5 of them minus 0.9 of them, and hopefully you say 5.6 of them, right? 5.6 times 10 to the 5th. By the way, you can also put your calculator in the scientific notation, but most of you need to learn how to use your calculator, so you really don't know how to do that either. But you should know these concepts, and then you can handle everything. Okay, so with C, this first one really isn't in proper notation, but it doesn't matter because it's not a final answer. So the powers match, right? We're good to go. So 21 and 2.1 is 23.1 times 10 to the negative 8th, right? Can we leave our final answer like that? No, because we have to put the final answer in proper scientific notation. Proper scientific notation, the first digit is always from 1 to 9. Always. Even if it's negative, again, it would be -1 to -9. It's got to be between 1 and 9, that first digit, and we got a 23. So hopefully you would agree we've got to move this decimal point one place to the left. And we need to have 2.31. But we just changed the number, and we don't want to change the value. So what would you do to the power of 10? Abigail? You would increase it. We moved the decimal point one place, so we would increase it by 1, and a -8 increased by 1 is a -7, right? If the front number gets smaller, the power has to get larger. If the front number gets larger, the power has to get smaller. If the power gets larger, the front number has to get smaller. If the power gets smaller, the front number has to get larger to keep the same value. Because those two are multiplied together. Okay, so last one. Go ahead and see if you can do D. I'm going to pause. It's terrible. I'm chuckling because 30 years ago when I started teaching, I would do a Cary Grant joke right now, but if I did it, you wouldn't even know what in the world I was saying. All right. It would be duty, but you don't have no idea what that means, right? Unless maybe you watched Andy Griffith and Gomer Pyle. So maybe you do, all right. But other than that, you wouldn't. All right, little Andy Griffith music. I like that. So what do we got? 0.065 positives and 9 negatives. So that is going to be -8.035. Huh? No, it's 9 negatives and 0.065 positives. You have a negative number and a positive number. These positives take away that amount of the negatives, leaving you -8.935. Yeah. Now I got you. All right, good. Thank you. All right. Yes, exactly. Right. Times 10 to the 9. All right. -8.935. I concur. All right. 0.035 positives wipe out that many of the negatives, leaving you -8.935. How many got that right? Okay, questions? Josh?
So would you be allowed to, instead of changing the 7 to the 9, change the 9 to the 7?
You could, but then when you're done, you're going to have to change that answer into proper notation because it's not going to be a proper scientific notation form. That's why I say always change the smaller to match the bigger, and a lot of times you won't have to change again. And again, you guys in your calculator, you're just punching in -9 plus 0.035, right? And it's going to tell you -0.935. All right. Then how about when you get to problems like this now? Okay, well, this is still the same concept. Look, these are like terms. Just treat them like an X or a Z. They're all the same. So then all we're doing is adding 4 of them plus 3 of them is 7 of them. Minus 12 of them is a -5 of them. It's not a final answer, and we're not really after a final answer. We're just after you seeing the analogy and adding the coefficients. Because again, this could have just been an N, an N, and an N, right? And what is N? 7 to the 11th. We okay with that? Did I make it concrete enough, I hope? Okay, so, all right, so here's a different scenario. Now we got a 2 to the 6th, a 4 to the 3rd, and an 8 squared. Can we do that with these? The answer is no, not in their present form. Can we, look, why would we give you the problem? Because obviously there's something we can do here. So what can we do? Anybody got an idea? What can you do with this thing? Can you make a 2 base into a 4 base? You could, but that's kind of a hassle. Can you make a 4 base into a 2 base? Isn't a 4 a 2 squared? And therefore now, isn't this middle one a 2 times 2 to the what power? 6, right? Exponent rule. X to the A to the B equals X to the A times B. Why do we learn all these exponent rules? Because they come up all the time. What are you going to do with the 8 squared? And 8 is a 2 cubed, right? So now we have a negative 5 times 2 to the 6th. And look at that. Now we can add them all up, right? 9 of them plus 2 of them is 11 of them. 11 of them minus 5 of them is 6 of them. And again, if we wanted a number, we could go full-fledged number here and multiply it out. But that's, if we were going to multiply it out with our calculator, we'd just do that from the beginning, right? Why even change anything? So that's how we're going to leave it. So we're just getting the concept of changing. All right, so try the last one. See what you can do with the last one. Okay, so how about negative 3 times 3 to the 8th plus 7 times 5 to the 3rd, right? You can't do anything with the 5 to the 3rd. How many got that? Okay. Do you agree the 9 to the 4th is a 3 squared to the 4th, which is a 3 to the 8th? And the 3 to the 8th is a 1 times 3 to the 8th. 1 of them minus 4 of them is a negative 3 of them. Look, there's technically one more thing I could do. If I really want to be excellent. What if I make the negative 3 a negative 1 times 3 to the 1st? Would you agree that's still a negative 3? What happens now when you do this exponent rule? So you get a negative 3 to the 9th, right? And I really could fool with the 2 that's part of this 6 if I wanted to, and make it 3 times 2 times 2 to the 6th, and really end up with 3 times 2 to the 7th. That's actually better. See how we're kind of playing with the exponent rules? All right, takes a little practice. So practice tonight, Josh.